Hello everyone, I am Saifullah and it is a privilege to present our research at the 27th International Conference on Knowledge-Based and Intelligent Information and Engineering Systems, KES 2023. Our study focuses on palm oil maturity classification using KNN boards based on RGB and LAB color extraction. Collaborating with the Institute of Computer Science at EGH University of Krakow, Poland, and the Department of Informatics at Universitas Pembangunan Nasional Veteran Yogyakarta, Indonesia. In this presentation, we have organized our findings into 4 case sections. We'll begin with a comprehensive introduction, setting the context and explaining the motivation behind our research. Then we'll delve into the methods and algorithms we employed, providing insights into our approach and methodology. Following that, we'll showcase the result of our experiments and analysis and engaging in an in-depth discussion about their implications. This will give us the chance to explore the significance of our findings and address any question that arise. Finally, we'll conclude with our key takeaway and conclusion, summarizing the main outcomes of our study. Introduction. Before we delve into the detail, let me provide you with an overview of the significance and key aspect of our study. Palm oil, as you may know, holds a remarkable position in Indonesian agriculture industry, boasting a staggering 58% global market share in 2019 by U.S. Department of Agriculture. The quality of crude palm oil is directly influenced by maturity level of the palm fruit, which can be categorized as ripe, intermediate, and unripe. To ensure precise classification of palm fruit maturity, we recognize the limitation of manual grading through visual assessment, which often leads to errors. As a result, we turned to the promising field of computer vision and image processing for more accurate and efficient solutions. One crucial step in our proposed approach is a color feature extraction, a powerful technique in image processing for effective classification. By incorporating pre-processing and segmentation method, we aim to enhance the accuracy of our model significantly. During our experiment, we made an intriguing discovery. The LAB color space showcased outstanding performance, outperforming the convolutional RGB color space is detecting palm fruit ripeness. This finding opens up new possibilities for refined classification techniques. So our research aimed to leverage the power of computer vision and image processing to address the challenges in palm oil maturity classification. Our proposed approach, backed by the superiority of the LAB color space, holds the potential to revolutionize the quality assessment of palm oil production. And this is focused on the KNN, the leverage of the power of KNN, particularly with sobel age detection for efficient palm oil ripeness detection. Our focus lies on RGB and LAB color space with pre-processing for faster processing. Our image processing pipeline encompasses pre-processing, segmentation, and color feature extraction using RGB and LAB, leading to KNN classification into 3 classes: unripe, raw, and ripe. Throughout this presentation, we will explore our methods, experiment results, insightful discussion, and key takeaways. So this is the part of we will to delve into the potential of our approach for accurately palm oil maturity classification. In this method and algorithm section, we illustrate the process of categorizing the oil palm dataset into the 3 classes: raw, unripe, and ripe. As shown in the first figure, these samples serve the basis for future analysis and classification. Additionally, we demonstrate the process of cropping oil palm images from the resized original image with its initial 300 cross 500 pixel in size to obtain cropped images of 19 cross 70 pixels. These cropping techniques accelerate the image processing while retaining crucial features for classification. Furthermore, we present samples of the cropped oil palm images, which are categorized as ripe, raw, and unripe, as depicted in this figure, the third figure. This image undergo color feature extraction, a crucial step in our algorithm to extract essential characteristics for classification. By following these methods and algorithms, we aim to achieve accurately and efficient oil palm maturity classification, contributing to the enhancement of crude palm oil quality and agricultural practice. Feature extraction. This study applies color feature extraction using two color models, RGB and LAB. In the RGB model, we calculate mean value for red, green, and blue channels. In LAB model, we use luminance L star and color component star A and star B for feature extraction, providing a perceptual uniform color space. Conversion formulae for LAB are derived from the CIAXYZ. These techniques enable us to effectively analyze and classify oil palm maturity level. Next, let's delve into the result and discussion to evaluate our approach and findings. Now, let's take a closer look at the question used for calculating the color feature extraction on the study. We have question 1, which used to calculate a mean of RGB color model. It helps us understand the average value for the red, green, and blue channels, providing insight into the color composition of the images. Moving on, we have a question for the LAB color model and CIAXYZ equation to H represent the conversion formula for LAB color model derived from CIAXYZ. The LAB model allows us to represent colors in the perspectual uniform color space, enabling more accurate analysis and classification of oil palm maturity level. This equation play a crucial role in our image processing pipeline and contribute to the success of our approach. In this table, we have samples of RGB and LAB color feature extraction for each oil palm maturity category, unripe, raw, and ripe. On the left hand side, you can see the original image, and on the right hand side, we have the corresponding image after converting them to the LAB color space. The RGB color feature extraction provides insights into the distribution of red, green, and blue channels, helping us understanding the color composition of each oil palm sample. On the other hand, the LAB color model offers the perspectually uniform color space, which enhances the accuracy of feature extraction and classification for oil palm maturity levels. By analyzing these color features, we better distinguish between different maturity categories, which is a crucial accuracy classifying the quality of the palm oil. Image classification is a fundamental task in the field of computer vision that aims to recognize and categorize objects present in images using various algorithms. In this study, we employ the KNN snake pores or KNN algorithm for image classification, which is a popular machine learning techniques. KNN operates based on the principle of finding similarities between new data points and existing data point in the dataset. It classifies an image by comparing it with its k-nearest snake pores in the feature space. The term k refers to the number of neighbors used for classification, and it is a hyperparameter that can be adjusted for optimize the algorithm's performance. So the illustrate can be shown in this figure. KNN is considered a lazy learner as it does not explicitly learn a model during the training phase. Instead, it stores the entire training dataset and makes prediction based on the distance calculation, typically using the Euclidean distance. Results of image processing and color feature extractions. The original images are pre-processed and segmented to extract color feature of objects. Segmentation with thresholding is applied to obtain white background and isolate palm oil objects. Resizing the image to 300 cross 500 pixels accelerates the process while maintaining object identification. Previous feature illustrate image with RGB and LAB color composition after feature extraction, and the LAB methods involve converting RGB to a new image using equation based on the previous table, and LAB metric representative preview provide three color components as demonstrated in a table for the next slide. This is the sample representation of LAB color space, LAB value based on unripe palm oil images with the row and the column of each images. So they have three level or three channels, L, A, and B, based on the convert by the RGB to LAB color spaces. The KNN classification process involves scenario with K is 1 to 9. The Euclidean distance is calculated on the new data based on the equation to perform the classification. So the figure A displays the accuracy for difference K in KNN and RGB. The optimal value of K is a 5, achieving an accuracy of 97.77%, while the average accuracy is 95.4%. And the figure B shows the result of KNN LAB with the best accuracy being 97.77%. So the KNN LAB is higher than KNN RGB. This is the result of calculating the key for cross-validation value for KES 5. Key for cross-validation used for data validating by splitting into training and validation sets. So the feature extractor that we are used is the by color extraction, RGB and LAB. RGB model achieved best accuracy at K is 4 and LAB at K is 1 and 5, and the average accuracy for the LAB in the KNN is 90.5% and RGB is 85.6%. Purpose method test with brightness variations, image rotation, and resizing, and LAB shows greater consistency in the color characteristic extraction compared to RGB. This is the conclusions. So the feature extraction and classification methods contribute to oil palm maturity identifications. KNN LAB achieves better accuracy, 2% higher, and validation result 4.8% higher than KNN RGB. So KNN LAB recommended for oil palm maturity classification with over 97% accuracy at the K is 5, and the feature work explore other color feature extraction method like YCBCR, HSV, YUV, XYZ for optimal RGB conversions, consideration of other machine learning methods, and bio-inspired agent-based algorithm for optimization in the future research.